Okay, so in this short video clip, we're just going to have a talk about detecting the speed before we actually collect the measurement. Machines today are becoming more frequently variable in control. Their speed varies due to process conditions, and we need to correlate vibration data with speed. So it's possible before we take our vibration reading to collect the speed, maybe via an optical tacho, but that means we need reflective tape on the shaft. Or we could go to the panel room and maybe read it from the frequency control system and then punch it in manually. Here we're going to talk about two methods, one of which uses the FFT itself to work out the rotational speed at this particular moment in time. And secondly, we're going to use a laser sensor pointing at the end of this cowling, firing into the fan itself without any reflective tape. So there's no need to stop the machine. We can do it in full flow without any interference. So initially we're going to go into the method to derive the speed from the spectrum itself without any speed reference. We're going to take a low Fmax FFT, and via an algorithm we're going to look for, if you like, harmonic activity around what would be the 1x peak, and hopefully that will self-detect the speed for us. So here we go. So one of the important things as well is obviously load. If the load varies radically and it's possible to easily store the load, we would correlate that with our results. So I'm being asked for the load. I'll just say it's 100% today. And the speed, this machine's rated at 1480, but I don't think it's running quite at full speed. So I'm going to type in turning speed detection, approximately 1350. That's an approximation. I'm going to hit the enter button, and that's going to go away and collect an FFT up to about 240 Hertz, and it's found a rotational peak at 1287 RPM with some very low harmonic activity of that frequency. There's nothing else nearby that I could mistake for the speed, so I'm quite confident that the running speed today of this pump motor system is 1287 RPM. So I'm just going to accept that, and the default speed that will be stored for the collection set now forward will be 1287 RPM. So just collect my data as I normally would. So the speed's stored at 1287. To go back on that, maybe I want to be using a laser sensor. So I've just flicked the lid of the laser sensor down, and I'm going to go back to the previous screen on the location we're measuring, and repeat the same exercise, this time using a laser sensor. So here we go again. I'll accept the load at 100% today, and this time I'm going to choose, instead of turning speed detection as before, we're going to choose laser speed detection. So it needs to know an approximate window of speed. 400 to about 1500 is the speed range I believe it's running today. And I'm just going to switch on the laser, obviously safety precautions in place at all times. And I'm just simply going to point the laser through one of these gauze is in the guard here to reflect off of the actual fan that's inside, and hit the enter button. Just concentrating on the instrument for a moment, guys, so I haven't forgotten you're there. Okay, so I've got a lovely spectrum here up to about, what's that, 400, about 450 Hertz roughly, 1500, 15,000 CPM, sorry. Sorry, 250 Hertz. And I've got a peak here that's been located at 1290. 1290. The previous method was 1287. This has picked it out at 1290, to be honest, 0.53 RPM. And there's clear harmonic activity. That laser sensor, without any tape, has given me clear evidence of what the speed is today, no interference, and I'm simply going to save that and store my data correlated to the correct speed today. So we're good to go.